Today I'm going to be showing you how to solve question 1 of the 2003 College Board AP Free Response section of the AP test. Question 1. Aniline, a weak base, reacts with water according to the reaction represented above. Part A. Write the equilibrium constant expression Kb for the reaction represented above. Now, since we are working with a weak base, anytime you see that, you should think possible buffer system and always try using an ice chart. In an equilibrium constant expression, we omit solids and liquids and only include the aqueous solutions in this case. In the expression, it is always products over the reactants. We are working with a base, so the constant expression is Kb. Conveniently, they already gave us the equation, so our answer to part A is C6H5NH3 plus times the molarity of hydroxide over C6H5NH2 equals to Kb. Part B. A sample of aniline is dissolved in water to produce 25 milliliters of a 0.1 molar solution. The pH of the solution is 8.82. Calculate the equilibrium constant Kb for this reaction. Right now we are working with a weak base, and they are giving us the pH value. The first step, we need to convert our pH to pOH by using the pH scale equation. pH plus the pOH equals 14. When we subtract 8.82 from 14, we get 5.18 is equal to the pOH. Next step, to help us visualize it better, we need to get the molarity of the base and the conjugate acid in order to find the Kb. Initially, they've given us 0.1 molar of our weak base, and we have no product. We subtract x and add x to both sides. Now, at equilibrium, because x is so small, we can ignore it, and so we have 0.1 molar and x to be our products. In order to find x, we go back to that pH scale equation, and since we have the pOH, we can use the pOH is equal to the negative log of molarity of hydroxide. Get rid of the negative, raise it to the 10, and you get the molarity of hydroxide to be 6.61 times 10 to the negative 6. That is our x. So we plug that into our Kb expression, and we get our Kb to be 4.37 times 10 to the negative 5. Part C. The solution prepared in Part B is titrated with 0.1 molar HCl. Calculate the pH of the solution when 5 milliliters of the acid has been added. So our new equation is C6H5NH2, our base, plus the acid H+, yields C6H5NH3+, and Cl is not in our overall equation because it cancels out and is a spectator ion. Our first step is to convert everything into moles. So we get 0.005 moles of HCl and 0.0025 of aniline. Whatever the smaller number is what's going to run out first. So we subtract 0.005 to get nothing left over, all our acid is gone, and 0.002 moles of aniline still left. And whatever we do on the left side, we have to do on the right side. So we add 0.005 in our product. Our last step is to change everything into molarity, and because volumes are additive, we divide by 0.03 to get 0.067 of our aniline base still left and 0.167 molarity of our product. Now it's time to set up our buffer system. So our new equation is C6H5NH2 plus H2O yields C6H5NH3 plus hydroxide. And now we set up an ice chart. Using our calculated answers from above, we plug in initially 0.067 and 0.167. We minus x on the left side and add x on the product side. Because x is so small, we ignore it in the overall equation. So we're left with 0.067 at equilibrium, 0.167, and we don't know our hydroxide content, so that's x. In order to find x, we use our Kb from part B, 4.37 times 10 to the negative 5, and set up our expression. We plug in 0.167, we don't know x, and it's over the reactants, which is 0.067. We get our x to be 1.75 times 10 to the negative 9, and that gives you your molarity of hydroxide. Now that we have the molarity of the hydroxide, we can go back to that pH scale equation and find our pH. So we need to find our pOH first. So since we have the hydroxide, we take the negative log of 1.75 times 10 to the negative 9, and that gives us 8.75 for our pOH. In order to find our pH, we subtract from 14, and our pH is calculated to be 5.24. Part D. Calculate the pH at the equivalence point for the titration in Part C. So we use that equation from Part C, C6H5NH2 plus H plus yields C6H5NH3 plus. We convert everything into moles and use 0.0025 because that's what we started with our weak base. At the equivalence point, everything is used up, so at equilibrium we'll have nothing left, and since we're losing 0.0025, we're making 0.0025 product. And we divide by 0.05 liters because the volumes are additive, and that gives us the molarity of our product left over. Since we are at the equivalence point, salt hydrolysis takes place and reacts with water. So our product, C6H5NH3 plus, reacts with water to yield C6H5NH2 plus H3O plus. And we set up our ice chart. We take our calculated answer and put it in for the initial. We have nothing left, nothing to begin with, and we subtract x and add x on the product side. And since x is so small, we can ignore it in the equation, and we're just left with 0.05. In order to find x, we need to use our Ka expression, so we need to find the Ka. So we use the equation Kw is equal to the Kb times the Ka. Kw is always equal to 1 times 10 to the negative 14, and we use our calculated Kb from Part B, which is 4.37 times 10 to the negative 5, and we're solving for the Ka. We get our Ka to be 2.3 times 10 to the negative 5. So, since we have our Ka, we can use our expression x squared over 0.05 is equal to our Ka 2.3 times 10 to the negative 5. From there, we get x to be 0.001, which is equal to the molarity of H3O+. Since we have the molarity of H3O+, we can use take the negative log in order to get our pH. When we do so, we get our pH to be 2.96 at the equivalence point. Part E. The pKa values for several indicators are given below. Which of the indicators listed is most suitable for this titration? Justify your answer. Since at the equivalence point our pH was acidic, the best indicator is erythrosine because the pKa is closest to the pH at the equivalence point. Erythrosine has a pKa of 3 and our pH is 2.96,